Hey guys, welcome back to another video, and today would be covering more basics of graph theory. So from part 1 we learned a few things. So the basics of vertex, edges, what are neighbors, and the degrees related to it. Or no, so we didn't discuss about degrees. So we discussed about components, which are an essential part of graphs. So we'd be discussing about degrees and all that other related stuff, so the basics that would lead us into our next topic, which would be extremal graph theory. So the degree of a node, so it represents how many nodes a particular node is connected to, so how many neighbors it has. So let's say we have a graph. A has B, C, D, E and F. So when we say degree of A, so this is how you write a degree of a certain node. So degree of A is only 1 because A is connected to only one node, right? On the other hand, if you look into degree of B, it is connected to 1, 2, 3, 4 nodes. So degree of B is 4, and similarly degree of C is 2, degree of F is 1, and so on, right? And the number of nodes inside of a graph is represented by this symbol, so V. So V tells us how many nodes there are inside of that graph. So in this case we have 1, 2, 3, 4, 5 and 6. So this would be 6. And the number of edges represents, so this represents the number of edges inside that graph. So we have 1, 2, 3, 4, 5. So you have 5 edges. And when we talk about edge set is basically all the edges in a set format. So we have A, B, right? So node A to B. Let's just write them in the proper order. So A to B, we have B to D, we have B to E, and so on. So this is basically called the edge set. So one of the important things that you would be needing is the maximum and minimum number of degrees side of a graph. So the maximum and minimum. So the maximum, the minimum number of degrees are represented via these symbols. So delta G represents, so the capital delta G represents maximum degree and small delta G represents minimum degree. So if you look into the graph, the minimum number of degree we have is 1. So only A is connected to B. This is 1 degree, right? So this is the minimum number. However, the maximum number is B, where we have 1, 2, 3 and 4. So this is the maximum number of degrees that any one of these nodes has. And let's just look into one small thing here, which is called a regular graph. So what is a regular graph? A graph where all the nodes, they have the same amount of degree. So this is an example of a regular graph where we can see A has the minimum degree of 2 and the maximum degree of 2, and similarly B also has a minimum maximum of 2, D has a minimum maximum of 2, C also has a minimum maximum 2. So all of them, they have the same value, right? So this is called a regular graph, and this can be said as K regular graph, where K represents the number of vertices they have in common. So let's say we have, in this case, so in the previous example, so this case all of them, they had 2 degrees each, right? So C, D, A and B, all of them, they had 2. So this is a 2 regular graph. And in a situation where we had, let's say A has 3 degrees and similarly B has 3 degrees, then that would be a 3 regular graph. So we're almost done with all the basic stuff, and there are a few top things that we need to talk about. So one of them is a walk. So let's just draw a graph. So this is the graph, right? So a walk is the vertex sequence of the graph that is followed while traversing the whole graph. So I know it's a bit complex to understand. So basically, let's say we start from A, right? From A to B, B to C, C to D, then we go back to A, then from A we go to E. So we traverse the whole graph but in a sequence, right? So we went from A to B to C to D, then we went back to A, then to E. So this is called a walk, where we are basically looking into our traversal path. So which nodes that we took to go from, let's say, one place to another. Now we have a path. So what is a path? So a path is basically a sequence of nodes that you traverse through. However, in this case we do not have any repeated vertexes. So we let's say go from A to B to C to D, and we stop. So A to B to C to D. Here, do we have any vertices that are repeated? No. So this is then called a path. If you look at the previous example here, we go from A to B to C to D. All of this is okay. We are not repeating any paths. However, when we go to A, we are not repeating any vertices. However, when we go to A, we are repeating the same thing. So we already went to A, right? We are repeating A again. So this is, in that situation, that becomes a walk rather than a path. But when we do not have any repetition in vertices, that becomes a path. And finally, we have a trail. A trail is a type of walk that doesn't have any edges repeated. So what do I mean by that? So let's just make this a bit clearer. Right, so as I said, trails cannot have any edges repeated. So let's say we go from A to C, C to B, B to A again, A to E, E to D, and D to C. So what path did we, so what is our traversal here, right? Because path is a different term here. Anyway, so A, we went from A to C, C to B, B to A again, A to E, E to D, D to C. See here, in trails we do have vertices that are repeated. However, we do not have paths that could be we do not have edges that could be repeated. So here we can see that from A to C, right? C to B, this path wasn't traversed. But if you go here, we are visiting A. In this case, when we are visiting A again, so this would be A, C and B, right? This wouldn't be a path because we are visiting A again. However, when we are talking about trails, this path wasn't visited. Even though the node A was visited, we are not looking into repeated vertices. So A was visited, that's okay. From A to E, this edge wasn't visited. So D to C, this was also not visited. So all of these nodes, all of this traversal, we can see that there are no edges that are being repeated. That's why this is a trail. So what is a closed walk? So a closed walk is where we start from one node and we go, we traverse all other nodes and come back to the same node again. We go from A to B, B to C, C to D, D to E, and we come back to A again. So we are starting from A and we are ending at A2, right? So this is a closed walk. So in a closed trail or circuit, if you remember from trails, that we cannot have edges that are repeated, right? So this is the same thing. If we look into, let's say, another example, here we can see we can go from A to B to C, and from another path we go back to A. So this is a closed trail, or which is also called a circuit, Here we are not repeating any other edges, we are just taking different edges to reach to the same node again. However, if we did this, we go from A to B and take the same path, go back to A. This wouldn't be a closed trail or a circuit. Finally, we have another topic, which is, these are easy because we already covered them but we didn't know the name. So this is a trivial graph. Trivial graphs are graphs that do not have any edges, so we do have only vertices, right? So there are three components here, so we have three vertices that are not connected to one another. So this is a trivial graph. And finally we have isolated vertex. So it's a vertex that doesn't have any edges. So let's say we have a connection here. Here in this case we have two components in the graph, right? One is this one, another one is this one. A is not connected to anyone, so this would be an isolated vertex. However, in a situation where, let's say, A, B, D and C, this is a graph, there are two components here, but none of them are isolated vertexes because all of them do have one edge or a connection, right? So in this case, A is the isolated vertex. Now this is the final topic of the video, so cut vertex and cut edges. So cut edges, so we talk about cut edges first. So let's say we have this graph and a cut edge, which is also known as a bridge. So a bridge is such an edge where if you remove that edge, the graph would be disconnected. Let's say this is the whole graph, and in this graph everything is connected, right? This has only one component. All the edges, all the vertices, they're connected, and there's no subgraph here. There's no concept of subgraphs. However, let's say we remove this, then what happens that is we do have two components, because these two are then becomes subgraphs, right? So this edge was the bridge that connected these two subgraphs together to make only one component. So this is what a cut edge or a bridge is. However, a cut vertex, let's just look into an example here. So in this example we have this whole graph, right? There only one component and there's no subgraph here. This whole thing, all the vertices, they are connected. However, let's say we remove this vertex, the middle one, in between these two, right? If we remove that vertex, what happens is that the graph is disconnected. We have two separate components, so one component, then this is like another component, and we have two separate subgraphs, right? So this whole vertex was the only thing that was connecting the two subgraphs together. So this is called a cut vertex or an articulation point. So I hope you guys did like the video. If you liked it, do leave a comment and a like. That helps me a lot. Thank you for watching.